We are nearing the end of chapter 4, 4.8. We will have a test either Friday or Monday.
Can we take it Tuesday?
No. Either Friday or Monday. Okay? So, today we're talking about 4.8, analyzing graphs of polynomial functions. So we got some vocabulary words over to the right. Isn't this fancy? It's not fancy.
Honestly,
Paper's not fancy.
doing this.
Local maximum, local minimum, increasing, decreasing. We'll learn what those things are today. Our learning goal, I can look at a given graph of a polynomial function and identify domain, range, intercepts, zeros, relative maxima, relative minima, and intervals of increasing and decreasing. Question. Okay. So, let f of x equal a sub n, x to the nth power, plus a sub n minus 1 times x to the n minus 1 power, so on and so forth, be a polynomial function. The following statements are equivalent. So these statements are equivalent. 0. K is a 0 of the polynomial function f. Factor. X minus k is a factor of the polynomial f of x. Solution. K is a solution or root of the polynomial equation f of x equals 0. X-intercept. If k is a real number, then k is an intercept of the graph of the polynomial function f. The graph of f passes through k, comma 0. So those statements are all equivalent to each other. And everyone should have that on their paper, correct?
Yes, sir.
Perfect. So we call solutions, zeros, factors, x-intercepts, roots. They all mean the same thing. So I'm looking at a graph. Wherever my x-intercepts are, the x-intercepts are my solutions. Or our zero, our factors, our roots. Any questions about any of that? We're okay with that? Okay, we're okay with that concept. Number 1, graph the function f of x equals 1/6 times x plus 3 times x minus 2 squared. It's the very next box on your paper that I gave you.
Do we put this in our graphic calculator?
No, we're actually going to graph this one without the graphic calculator. Oh. So,
Pretty easy.
what do I know about like my solutions, my factors, all that good stuff? Are my solutions the same thing as my factors?
No.
Are these equivalent statements? Yes, they are. So if I have a factor, I already know my solutions, right? Is this in factored form? Is this completely factored out where I cannot factor it further?
I guess.
Yeah. Can I factor x plus 3 further? No. Can I factor x plus or my x minus 2 further? No. So this is in factored form. X plus 3 is a factor. X minus 2 is a factor. Right? So what are my solutions here? Those are my factors, but I can use those to get my solutions, right? By setting them equal to 0. How do I get x by itself on the first one?
Subtract factors.
Subtract 3. So what does x equal?
0. Negative 3.
Negative 3. Add 2 over here. What does x equal here? 2. So x equals negative 3, x equals 2 are my solutions. What do I know about solutions and zeros and x-intercepts? They're all the same, right? So does that give me 2 points for my graph?
Yeah.
What are the 2 points?
Negative 3, 2.
Negative 3, comma,
2.
what?
0.
0. And 2, comma, 2, comma 0. They're my x-intercepts, right? So I can go over 3 on my x-axis, put a point. I can go to the left 3. I can go to the right 2 on my x-axis, put a point. Does everyone see how that gave me 2 of my points on my graph? My solutions are my zeros. My x-intercepts. Okay? Okay, the next thing I want to do, I want to get some more points around these points. So I'm going to make a table of values, and I'm going to plug in numbers that are around negative 3 and 2. Okay? So let me erase this right here. Let's make an XY table. Like I said, I'm going to use X values to plug in that are around -3 and +2. So I'm going to use -2, -1, 0, 1, and 3. Everyone okay with that? This is so I can get more points that are near the points that I currently have. Any confusion so far?
What does that even do?
Well, we're about to plug them in to our function to get the y value for each point. Okay? So I'm plugging -2 in for x. Just replaced all my x's with -2. What's -2 plus 3? 1. What's -2 minus 2?
-4.
-4. And what's -4 squared? -4 times -4?
-16.
No.
16.
16.
Oh, you're right.
1/6 times 1? 1/6. And 1/6 times 16. Give it to me as an improper fraction.
Hold on. I'm going to do this in my next one.
Uh-oh, our graphing calculators don't do it for us.
Why?
Oh, I guess we're going to have to do it on our own. How do I multiply fractions?
Don't you make the other one a fraction?
Yeah, I just did.
Is it the one thing? Yeah.
Huh?
Like cross?
Oh, don't tell me the butterfly method.
Well, I don't know.
I just multiply straight across. So what's 1 times 16?
16.
16. What's 6 times 1? Let's reduce it. What are 16 and 6 both divisible by? 2. What's 16 divided by 2? 6 divided by 2?
3.
3. There we go. And what would that be as a mixed number? Ooh, testing all your elementary math skills.
Is it 2?
How many times does 3 go into 8?
Isn't it 2 2/3?
There you go, 2 2/3. 3 goes into 8 2 times, that's my whole number. My remainder is what? What's 3 times 2? 8 minus 6. That's where I got the numerator of 2. Keep the denominator the same. Okay? So 2 2/3. We're going to do this for every single one of these numbers. Plug them in. I'm going to skip a few steps as I'm plugging in. Like I might do the exponent while I'm multiplying, if everyone's okay with that. Just to make it a little quicker. Okay, plugging in -1. What's -1 plus 3?
Negative, no, just 2.
Positive 2. And then what is -1 minus 2?
Negative
-3, and then -3 squared.
9.
9. 1/6 times 2.
Is it
1/6 times 2. 1/3. And then 1/3 times 9.
3?
3. Questions how I got that? Is everyone okay if I skip steps like that? Everyone see what I'm doing? Paying attention to what I'm doing? Okay, plugging in 0 for x. What's 0 plus 3? 3. What's 0 minus 2? 0 minus 2? -2. -2 squared. 4. 1/6 times 3. 1/2. 1/2 times 4. 2. Everyone still with me? I'm moving too fast for anybody. Okay. Plugging in 1. What's 1 plus 3? 4. What's 1 minus 2? -1. -1 squared. 1. 1/6 times 4. 2/3. 2/3 times 1. 2/3. And last but not least, plug it in 3. What's 3 plus 3? 6. 3 minus 2. 1 squared. 1/6 times 6. 1. 1 times 1. Questions how I got any of my y values? Now I'm going to plot these points on my graph. Sorry it's so small up here, but you guys have the graph on your paper. So I'm going to go left 2, up 2 and 2/3. So that's 2/3 of the way between 2 and 3. Okay? So left 2, up 2 and 2/3.
Why did you go left 2?
Because it's -2, my x value. Now I'm going to go left 1, up 3. Just plotting these points, graphing these points. I'm going to stay on my y-axis and just go up 2. Go right 1, up 2/3. And then right 3, up 1. Everyone see the points on there? Everyone get their points graphed. When you graph them, does it look similar to what I have? Should be pretty close. Okay? Now, do you guys remember when we talked about in behavior? I think it was last chapter. In behavior of graphs. When we're talking about in behavior, we're talking about the degree of our function and the leading coefficient. We talked about the leading coefficient either being positive or negative, and then the degree being even or odd. You guys somewhat remember that? There was a chart that said f of x goes to positive infinity as x goes to positive infinity, so on and so forth. You guys somewhat remember that. You might need to grab that chart out of your book or out of your notes at some point so you have it. If I were to multiply my function out, would my leading coefficient be positive or negative? Anyone have any ideas? Because this would be 1/6 times x plus 3 times x minus 2 times x minus 2. Would anything like that make my leading coefficient negative at all? No, it wouldn't. So my leading coefficient is going to be positive. What's the degree of my polynomial? The biggest exponent. If I have x plus 3 times x minus 2 times x minus 2. 3, right? Because when I multiply 2 sets of the parentheses, I'll get a quadratic. Then I got to multiply that other parentheses to make it a cubic function. So my degree is 3, which is odd. My leading coefficient is positive. So my end behavior, you would see this in your chart if you were looking at your chart, is this. F of x, my y values go to positive infinity as x goes to positive infinity. And f of x, my y values go to negative infinity as my x values go to negative infinity. That's going to be my end behavior. So as my x values are getting bigger, my y values are also going to get bigger. So it's going up and to the right. As my x values are getting smaller, my y values are also getting smaller. So it's going down and to the left. That's what that's saying. Does that make sense? So knowing my end behavior, I'm going to connect my points with a curve and make sure it's going up and to the right and down and to the left. Does that make sense? So up and to the right. And start connecting my points with a curve. And down and to the left. How's that graph, Bella? Better than my other ones, huh? And so now I have graphed my function. Does everyone see how we got that? Find your zeros. Those are your x-intercepts. Plug in points that are around those numbers to get more points. Use your in behavior, connect your points. Questions on example 1? We awake? Okay, can I move on? Oops. Golly. There we go. Okay, let's talk about the location principle. If f is a polynomial function and a and b are two real numbers such that f of a is less than 0 and f of a is greater than 0, then f has at least one real 0 between a and b. This one should be, golly, I keep doing that. This one should be f of b. So if my f of a is less than 0, f of b is greater than 0, then f has at least one real number between a and b. So here's what that is essentially saying. I have an x value of a, and let's say the y value that corresponds with that x value is a negative number. It's going to be somewhere down here. Right? And then I have an x value b. The y value b is a positive number. Then it's saying f has at least one real 0 between a and b, which makes sense because these points would have to connect. And is it crossing the x-axis between those 2 points?
Yeah.
Yeah, it is. Right? So if I have one that has a y value that's negative, one that has a y value that's positive, somewhere between those 2 points there's got to be a real 0 because it's crossing my x-axis. That's essentially what that's saying, the location principle. Does that make sense?
So you're trying to find out what number that is?
Well, I can use this information to know that, well, we'll look at number 2. Okay, hold on one second. So it says, find all the real zeros of f of x equals 6x cubed plus 5x squared minus 17x minus 6, given the following table of values. So this table of values goes with our function. Okay? So, do I have an a value or an x value that has a negative y value, and then immediately after that x value, the next x value has a positive y value? Huh? Well, let's look at the first two. -2, -1. Is the first one negative and the next one positive, the y values? No. One's 0, one's positive, right? What about between the next two? Is the first one negative and then the second one positive? No. But between these two, is the first y value positive and the next one, or first one negative, second one positive? No. What about between these two? Is my first y value negative and my next one positive? Yes. So based on the location principle, I know there must be a real solution between 1 and 2. Okay? Because it's going to cross the x-axis somewhere between 1 and 2. Does that make sense? How do I know what possibilities that might be? Because there's an infinite number of numbers between 1 and 2.
What?
We were talking about it before class. How can I find a possible solution? RRT.
We're not doing that now.
Yeah, we are. Rational root theorem. So let's list factors of our constant. You guys love the rational root theorem. My constant's -6, correct?
Where'd you get -6 from?
It's my constant for my polynomial. Right? Rational root theorem says possible solutions are factors of my constant over factors of my leading coefficient, correct?
Yeah.
So let's list factors of -6. What are they?
-6. Over 6.
1.
Plus or minus 1.
2.
Plus or minus 2.
3.
Plus or minus 3.
6.
Plus or minus 6. Is that all? Yep. What's my leading coefficient? 6. So let's list factors of 6. It's the same ones for negative 6, correct? You okay with that? So remember, for the rational root theorem, if I put the factors of my constant over the factors of my leading coefficient, those are possible solutions for my polynomial. Do you guys recall that? Hopefully. So I need to put all of my top factors over all of my bottom factors. So I get plus or minus 1 over 1, plus or minus 2 over 1, plus or minus 3 over 1, plus or minus 6 over 1. So I put all my top ones over my first bottom one. Now I got to put them all over plus or minus 2. Fun stuff. So plus or minus 1 over 2. Plus or minus 2 over 2. Do I already have a version of 2 over 2? Yeah, it's plus or minus 1 over 1, so I don't need that one. Plus or minus 3 over 2. And plus or minus 6 over 2. Do I already have a version of 6 over 2? Yeah, it's 3. I don't need that one.
Where?
6 over 2 is 3 over 1, right?
Yeah, but what do you...
I already have a 3 over 1. Right? So I put them all over 2. Now I got to put them all over 3. Plus or minus 1 over 3. Plus or minus 2 over 3. Plus or minus 3 over 3. Do I already have 3 over 3? Yeah, that's 1. Plus or minus 6 over 3. Do I already have that? Yeah, that's 2. So I put them all over 3. Now I got to put them all over 6. Plus or minus 1 over 6. Plus or minus 2 over 6. Do I already have that? Yeah, that's 1/3. Plus or minus 3 over 6. That's 1/2. Did I already have 1/2?
Yes.
Yeah, I do. Plus or minus 6 over 6. I already have a 1 over 1. So the ones that are not crossed out are possible solutions to my system, or not my system of equations. That's algebra 1. We're talking about system of equations in there. Possible solutions of my function. Where do I know I have a real solution? Between what and what? 1 and 2, based on my location principle, right? So which of these possible factors down here, possible numbers, is between positive 1 and positive 2?
1/2.
Not 1/2. That's between 0 and 1.
3 over 2.
3 over 2, right? Because 3 over 2 is 1 and 1/2. So let's test 3 over 2 to make sure that it is a solution to my polynomial. How do I test it? Synthetic division. You can use synthetic division with fractions. It's fun stuff. What are the coefficients of my function?
6, 5, negative 6.
6, 5, negative 6. How do I know if this is going to be a factor or not?
F it times 0.
Yeah, I get a remainder of 0, right? So, bring down your 6. What do I do with that 6? Multiply by 3 over 2. What's 3 over 2 times 6? 9. The 2 and the 6 reduce to 1 and 3. 3 times 3 is 9. What's 5 plus 9? 14. What's 3/2 times 14? 21. 2 reduces to 1. 14 reduces to 7. 3 times 7 is 21. Negative 17 plus 21. 4. 3/2 times 4. 2 reduces to 1. 4 reduces to 2. What's 3 times 2? 6. Negative 6 plus 6? 0. So it's 3 over 2 a solution? Yes, it is. But it wants me to find all the real zeros, not just one of them, right? So hopefully I don't have to do the rational root theorem again. Let's see if we do or not. I'm going to erase my rational roots over here. How would I write 3 over 2 as a factor?
1 and 1 half.
No. I'm talking about like in parentheses with an x. Would it be x plus 3 over 2 or x minus? X minus. I need more room. X minus 3 over 2. If I pull that out as a factor, what's my other factor over here? My other polynomial. Using the synthetic division I just did. What's my leading coefficient of this new polynomial? 6. X to the what power? What's 1 less than my original polynomial? 2. Because my original polynomial, the degree is 3. What's the next term?
14.
Plus 14x. Plus 4. So everyone see where we got that from? We got those coefficients from my synthetic division. Okay? Now, can x minus 3 halves be factored further? X minus 3 halves. No. What about 6x squared plus 14x plus 4?
Yeah.
Probably. Let's try it. What do I need to factor out? 2. It's got a GCF of 2, correct? Golly. We having fun yet?
No.
Yeah, we are.
How come we don't get to play ultimate football?
Shh. Let's not talk about that right now. If I factor out a 2, GCF of 2, 2 times what will give me 6x squared? 3x squared. 2 times what will give me 14x? 7x. 2 times what will give me 4? 2. Any questions on how I factored so far? Can 3x squared plus 7x plus 2 be factored further? Yeah, it can. Let's keep factoring. And to clean the left part up a little bit, I'm just going to distribute my 2 through this set of parentheses. Everyone okay if I do that? What's 2 times x? 2x. 2 times negative 3 halves.
Is it negative 1 or 2?
Both the 2's reduced to 1. What's 3 times 1? 3. So we're saying 3x squared minus 7 or plus 7x plus 2 could probably be factored further. So we're probably going to have 2 sets of parentheses here. How am I going to factor 3x squared plus 7x plus 2? Slide and divide. Bring my 3 over, multiply by 2. It's 3 times 2? 6. Now let's factor this. What's the variable I'm dealing with? X, so the x goes in the first part. I have a plus sign in front of my c value, so my sign's going to be the same or different. Same. If they're the same, what are they both going to be? They're both going to be addition. Now I'm looking for numbers, 2 numbers that would multiply. Give me 6. Add to give me 7. 1 and 6. 1 and 6. And what's the last part of slide and divide? Make sure we're awake, paying attention. There's kind of some difficult stuff, so I'd hate for you to miss out on it and not know how to do it. What do we divide by? 3, because that's the number I slid over and multiplied by earlier. Can I simplify 1 over 3 anymore? So what do I do with that 3?
Bottoms up.
Bottoms up, bring the 3 in front of the x. 3x plus 1 is one of my factors. Can I simplify 6 over 3?
Yes.
What is it? 2. Does everyone see how we factored 3x squared plus 7x plus 2? We okay so far? If you have questions, please ask questions. Can any of these polynomials that I have be factored further? 2x minus 3, 3x plus 1, or x plus 2? No, they can't. We're almost done. We're almost there. I can see the light at the end of the tunnel. How do I now find the solutions given these factors?
Put them as 0.
Set them equal to 0. 2x minus 3 equals 0. 3x plus 1 equals 0. X plus 2 equals 0. And after I solve these 3 equations, it will give me the real zeros of my polynomial. First equation, how do I get x by itself? Add 3 to both sides. 2x equals 3. And getting x by itself, divide by 2, so I get x equals 3 halves, right? Which we already knew that one based on our location principle and our rational root theorem and our synthetic division, correct? But we use that to help us get these other 2. It's my first step on this next one.
Subtract 1.
Subtract 1, so 3x equals
-1.
-1, divided by 3, x equals -1/3. Questions there? And last one, how do I get x by itself? Subtract 2, so x equals -2. Based on my fundamental theorem of algebra, how many solutions do I have? 3. Did I find our 3 solutions? Yes, I did. And they all happen to be real zeros. None of them are imaginary. Questions how I found that? It's good stuff, huh? Algebra 2 is pretty fun.
Yes, sir.
A lot of hard work pays off, right?
Pays off what you need.
Questions on that? Okay, can I move on?
Sure.
All right, flip it over. Okay. These definitions right here come straight from your book. Talking about turning points, maximums, minimums, increasing and decreasing. Let's see, the y-coordinate of a turning point is a local blank of the function when the point is higher than all nearby points. So if it's higher than all nearby points, do you think it's a local minimum or a local maximum? Maximum. If it's higher than everything else, it's a maximum. So in my blank, I'm going to write maximum. Questions on that? The y-coordinate of a turning point is a local blank of the function when the point is lower than all nearby points. What do you think I'm going to put there? It's lower than all the other points around it. Maximum or minimum? Minimum. Any questions about that? Now let's talk about turning points because the first 2 were talking about turning points, right? Turning points occur when the graph changes direction. So that's where it goes from increasing to decreasing. That's what we call a turning point. Going from increasing to decreasing. Or when it's going from decreasing to increasing, that's a turning point. So when my graph changes the direction that's going. Does that make sense? Turning points occur at our local maximums and our local minimums. Okay? The graph of every polynomial function of degree n has at most n minus 1 turning points. So we'll not have, so if I have a degree of 3, what's 3 minus 1? 2. That graph would have at most 2 turning points. Does that make sense? If a polynomial function of degree n has n distinct real zeros, then the graph has exactly n minus 1 turning points. So if our degree is 3, what's 3 minus 1? 2. And it has 3 distinct real zeros, that one's going to have exactly 2 turning points. Okay? Any questions about that? Okay, our last examples here. Identify the x-intercepts, the turning points, the intervals of increasing versus decreasing, and the local maxima and minima. It also wants our y-intercepts. So what is an x-intercept just in general?
When it like crosses the x-axis.
Where my graph crosses the x-axis. So how many do I have here? 2. What are my x-intercepts? -4, -2. So I'm going to put -4, comma 0. I'll put the ordered pairs of them. -2, comma 0. Everyone see that that's where it's crossing the x-axis. Okay, what's a y-intercept in general? Where my graph crosses the y-axis. Where is this one crossing the y-axis at?
8.
-8. So what's the ordered pair? 0, -8. Not -8, 0. Because you're not going left to right any, but you're going down 8 to get that ordered pair. Any questions so far about our x or y intercepts? Okay, increasing. Does everyone know what I mean when I say the graph is increasing or decreasing? We read it from left to right. If it's going uphill from left to right, it's increasing. If it's going downhill from left to right, it's decreasing. Does everyone see that? So here, it's increasing, 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 because it's going uphill, left to right. Then it hits here, and it starts decreasing. It's going downhill from left to right. Does that make sense? So I want the interval for when it's increasing. So what's my interval for when it's increasing? Huh? 1? Remember reading it from left to right. So which x value does it change from increasing to decreasing? What? -2. One more over. No, the other way. -3. Does everyone see that? Going from left to right. Once it hits the x value of -3, it starts decreasing. Right? Was there a starting point for it increasing? No, it's going on forever and ever and ever to the left, correct? So from -infinity all the way to -3, it's increasing. I would represent that by saying x is less than -3. For all values less than -3, it's increasing. Does that make sense? Is there any other part of the graph where it's increasing? No. So what would my interval be for decreasing? Here we go. X is greater than -3. Because from -3 to positive infinity, it's decreasing. Does that make sense? So what would that make my turning point? Where does it change from increasing to decreasing or decreasing to increasing?
-3, 1.
-3, comma 1. That would be right there. Does everyone see that? Once it hits that point, it changes from increasing to decreasing. So that's my turning point. Do I have any other turning points? No, that's my only one. What's my local max? My local maxima?
Is that it?
Huh?
Is it
-3, comma 1. Yeah, our turning points are either maximums or minimums. In this case, it's a maximum because this ordered pair is higher than all the other ordered pairs around it. Does that make sense? Do I have a local minimum? No, I do not. So I would put none. Questions on example 5? Okay, we'll do the last example tomorrow and get our assignment.
Awesome sauce.
You guys already have the assignment on your sheet of paper, bud. We'll work on it tomorrow. Don't worry about it. Trey, would you hit the lights, please? Come get my calculators back. Everyone bring them back. Doesn't matter what order, what row, just bring them back now. Are there any questions about our notes before I end the recording?